let's take a look at the branch where we set up our baseline classifier model. So I have modified a few of the scripts in this repo here, notably metrics, models, and train.py to set up this model. Let's start with metrics because it's short and sweet. So here I'm basically just defining this compute metrics function, and this is just going to return a dictionary where I've wrapped a couple of common classifier metrics from scikit-learn's metrics module. So really not too much to say there. Just if we want to add more metrics later, we can do so here, and it'll all be nice and cleanly contained within that compute metrics function. Let's look at our model definition. So I'm creating this class called baseline classifier. Suppose I can zoom in here a little bit. And this is going to contain an attribute, self.model, which is a dummy classifier. That's a class that comes from scikit-learn's dummy module, unsurprisingly. For this, we're going to specify a strategy and perhaps a random state. We'll see what those are in just a little bit. Now, because we need to cast our regression problem as a classification problem, we need to specify a way of turning those continuous values, number of upvotes, into a binarized label, yes or no. And what we're going to do for that is I'm defining this function threshold factory, which takes in a threshold argument. And basically it says this is going to be equal to, this is going to give us, for an input, the original upvotes, and our output will be an array of zeros and ones, where one means that it had more than some threshold number of upvotes. So by default, I'm calling that 10 upvotes, but we can change that later if we'd like, according to project requirements. In train.py, we can look at everything that happens when we want to train this model. Of course, we are importing our baseline classifier. We're importing the compute metrics function. We're importing threshold factory. We're also importing some nice stuff we defined in data.py. And we are going to set up our command line arguments. So we have to say things like the artifact name, the target column name, the strategy for our model. Again, more on that later, and a message. Again, that's like a sort of like a git commit message. It's so that when we log to Comet, we can sort our experiments or group them according to the message, right? Message like train baseline classification model, for instance. So when we run this script, we'll get our arguments, create an experiment, add some tags, just saying this is a classification, it's a train and evaluation run. We'll log some of our parameters for how we're instantiating our model. We'll get our data, we'll load our data, we will drop unnecessary or invalid rows of our data because we want to get rid of all those rows where there's no score. And then we can create our model. Again, this is just according to command line arguments. And we're saying the target transform for our model, the way that we turn continuous values into discrete classes is using our threshold factory with a threshold that we passed in the command line. So I could say, when I do my run, threshold 5, and then the target transform would say yes or no, this got more than 5 upvotes. So we'll then pop off our target vector from train.df, and we'll fit the model. And now that our model's fit, we can, of course, do our metrics. So here, we're going into experiment train and experiment validate. So these context handlers will append, train, and validate prefixes to these metrics when we compute them so that it's really easy to see what we're dealing with in the Comet UI. So we compute our metrics and we log them. For validation, we get Y validation off of valid.df. We create our predictions, compute our metrics, and log them. And after that, we just need to say, all right, what do we want the saved model path to be? We'll save the model to that path, and then we'll log the model using that path. And that's it. So if I wanted to run this, I could do something like the following. So I'm in this source directory. So train.py is right there. I could say Python train.py message could be something like train baseline classification model. I could say something like threshold. I want that to be 10. I could say something like strategy, and maybe I want my strategy to be prior, and so forth. And I could run this. And so I can do that, and we'll start seeing some of the output, but I've actually already run these experiments a couple of different ways. So we're going to switch over to the Comet UI to take a look at that. So here I've created a view, which I've called baseline classification. So I've set up the columns for this table to be those that are relevant to classification models. So we can look at the accuracy, loss, precision, and recall, and so forth. So I can see some of my runs here. Here's my original prior run, seeing that we get an accuracy of a little over 88%. Now that we see the pretty apparent differences in these metrics across the 3 different strategies, let's talk about what dummy classifier actually is. So just referencing the scikit-learn docs here really quick, when we specify a prior strategy, that means that after fitting, the predict method, which gives us predicted classes, returns the most frequent class in the observed Y argument passed to fit. So most posts get fewer than 10 upvotes. That's what we see in the training data. So when we learn that pattern, that means that from now on, every prediction is fewer than 10 upvotes. We are saying nothing will succeed. Very pessimistic model. What can you do? We also have the uniform strategy. So this is going to take basically a 50-50 coin flip every single time it has to predict whether or not a post will succeed. Each class has equal probability. And then we have the stratified approach, which sort of combines ideas from the previous 2 approaches. We use the observed class distribution. We see that 88-ish% of posts have fewer than 10 upvotes, fewer than or equal to technically. And then we use those frequencies as probabilities when we sample new rows. So I would say for every single row, there's a 12% chance I'll say that it will be successful. So this is making use of the observed class distribution like prior, but it is making a random prediction each time like uniform. So with all that being said, we can really quickly look at our metrics. Note, for instance, that promising altitude here, our prior strategy, has training and validation accuracies a little over 88%. That's because we have imbalanced classes, and that's the percentage of, or that's the proportion of zeros in the data. So we're always guessing 0 and we're right 88% of the time. Recall is 0 because we're never seeing those true positives. And precision is 0 because it's ill-defined, because we would have to divide by 0 here. For our other 2 models, the uniform one gets about 50% accuracy. That should stand to reason because we are flipping a coin every single time we're making a prediction. So half the time we're right, doesn't matter what the right answer is. Half the time we're right. And we can see what that does to precision and recall. And then the stratified one doesn't do quite as well on accuracy as prior because it's making mistakes on both types of cases, but it is recovering much better for the precision and recall than the prior one. This has lower loss than the uniform model. So in that sense, it is perhaps less wrong more often. And again, this just gives us a way of looking at how well we can do on this problem without using any information from the features. So as we keep going in this project and we start building models that actually use information in the headline or body or the time of day or the day of week or who posted what, now we know what to compare ourselves against.